So I think the initial setup is pretty straightforward, isn't it? So you simply go integral from somewhere to somewhere. Did you guys decide to do this in terms of x or in terms of y? In terms of x. Okay, so my limits of integration would be from 0 to where? 0 to 1/2, yep. Any questions on that part? If we're going to draw a representative rectangle, and it would be a vertical oriented representative rectangle sliding from left to right across the little region there. So we'd end it at x equals 1/2. And then the integrand would simply be the top minus bottom, or high minus low, depending how you want to look at it. So high, that would be, which one would that be, the sine or the cubic? On our interval, it's the sine, isn't it? Now once you leave our interval, then that changes. But on our particular interval, sine is the higher one. So it would be sine of pi x minus the lower one, which is 8x cubed dx. And that's it. That's a setup. What follows is somewhat challenging. I think I would encourage you all to split this integral up into two different integrals, because wouldn't it be fair to say that the first term of the integrand is going to need, like a Timmy messed up the chain rule adjustment?
Wouldn't you just use math 1?
I wanted you to try to do this without, for practice, right?
Oh, I just used
I would highly, I would definitely expect you to be able to do this without a calculator. So I thought we'd practice that. But if your calculator was active and you didn't use Math 9, you're unwise in that regard there. So let's go ahead and use simply pen and paper to do this. So I would split it up. Sine of pi x would have its own integral, and then 8x cubed would have its own integral as well, like so. Split it up into two different parts. So if we keep going here, I would need an extra factor of pi in here, so I'd need to multiply the outside by 1 over pi. You could do u substitution or the chain rule adjustment there if needed to do that. So in doing so, I would get 1 over pi times sine of pi x, evaluated from 0 to 1/2, minus the antiderivative of 8x cubed is 2x to the 4th. So that would be 2x to the 4th, also evaluated from 0 to 1/2. Still hanging in there? Any questions so far? Okay, so we just got a couple of FTC 1s to do. So it would be 1 over pi. And let's see, it'd be sine of pi over 2.
Hold on, will you integrate sine?
Oh, what am I doing? How about let's go with negative cosine?
Yeah.
Sorry, that's just a little oops there. Oops, let's make that a little bit wider. There we go. Negative cosine should go right there. There we go. Negative cosine. Okay, so negative cosine of pi over 2 minus negative cosine of 0 minus, let's see, it's going to be 2 times 1/2 to the 4th minus 2 times 0 to the 4th. So to finish this out, let's see here. Cosine of pi over 2? 0, yay. Cosine of 0. So it's really plus 1. So I'm getting 1 over pi times 1, so I'm just getting 1 over pi for my first term. Minus, well, let's see here, 2 times 0 is 0. 1/2 to the 4th is 1/16. 2 times 1/16 is 1/8. So I'm getting 1 over pi minus 1 over 8. Is that okay? So I wanted us to do that just for the reason of going through all the steps and getting a rational answer versus a decimal answer. So there you go. Any questions about that one? Okay, so we did skip number 3. Let's go back to number 3. You guys could flip back one spot in your notes, and we'll just, with number 3, we'll just, I think maybe we'll just set it up. So take a look at that. It says, sometimes it's easier to use a horizontal representative rectangle. I hinted at this yesterday. When we do this, the representative rectangle is no longer dx wide. It is how wide? dy. And so that's going to change everything. That simple fact is going to change everything else in the integrand. And the limits, everything is going to have to be in terms of which variable? Not x, because dy means everything has to be in terms of y. So really what determines the variable that you're going to use is the differential. If it's dx, everything's got to be x's. If it's going to be dy, everything's got to be y's. And there can't really be any mixing of those things to get things finished out. Make sense? Okay, so let's take a look at number 3 and we'll address the higher function question. Do you guys remember doing stuff like number 3? I mean, even like Greg, Michelle, and Will, did you do like functions of x in terms of y in pre-calc? Do you remember doing this? Okay, well, let's see how this graph looks. Let's go ahead and graph this out and we'll kind of see which function is higher and lower and how we'll set this up. So, the first one, x equals 3 minus y squared. If you were going to describe that, what would you describe it as? Parabola. Sideways though, right? Not an up and down, but a left-right parabola. Would this parabola be opening to the right or would it be opening to the left? Why do you say left? Negative y squared, right? So it's opening to the left. And then what does the 3 do to the graph? Right 3. There you go. So all of those rules that we normally learn for graphs of functions, whenever you flip it to be sideways, all those rules basically kind of get flipped on their side, essentially. And so you'd have a parabola, as some of you described, shifted right 3, opening to the left. So how about that? There's our parabola. And then the line x equals y plus 1. I don't know, we're so used to graphing y equals in terms of x. Why not just subtract 1 from both sides and do it that way? What do you think? So y-intercept would be -1, slope is 1. Okay, so I'll graph that kind of in the more normal fashion. Could graph it the other way if we wanted to, I guess, but I'm going to go with, let's see here, so it would have to be something like that. All right, so we're talking about this region right here. We were supposed to find the area of that region. So this is where we get into the idea of sometimes it's easier to use a dy rectangle. Let me try to explain why I think it's easier, and we'll go with it. So if I were to use a vertical representative rectangle, it would be doable. Y'all can't see that very well. Let me use a different color. So if I was to use a vertical representative, man, that doesn't work either. Let's see here. How about yellow? I bet you can see yellow. There we go. So if I was going to use a vertical representative rectangle, I'd be sliding from where to where? Left to right. So it'd be something like this. And so as I go on that first part of the region there, the left part, the top of the representative rectangle is determined by the line and the bottom is determined by the curve. That's not a big deal, is it? That's fine. But once I get over to this spot right here and move to the right of that, no longer is the top determined by the line and the bottom by the curve. Now the top and the bottom are both determined by the curve, aren't they? And that's actually doable. There's some symmetry there that we could use to make this a little bit easier for ourselves. It's not that that's impossible to do. It's just that we'd have to have a second integral, second integrand, second fundamental theorem of calculus part 1, and that's not necessarily the easiest way to go. The easier way to go would be to take that representative rectangle, instead of making it vertical, make it horizontal. I'll show you why in a second. Let me erase all this stuff. And something like this, I think would be easier. So instead of sliding from left to right, this is going to slide from top to bottom, or bottom to top. So it's going to look something like that as it sweeps across this region. So now, no matter where you are, isn't the right edge determined by the curve, and the left edge is determined by the line? Therefore, you just need one integral, one integrand, easier. Okay, does that make sense? Does it seem logical? I hope it does. So, all that to be said, do you see why this would not be a dx rectangle? It would be dy. And so because we chose horizontal and it makes it dy thick, that sets the course for the rest of our integrand. It means that everything has to be in terms of y, not just the dy. So let's set this up. Integral from where to where? How are we going to find the limits of integration? Use the graphs. Y coordinates of the point of intersection. That's right. So if we're going to find those coordinates, we don't have to use the calculator. We could just go by hand. We should erase. You ready?
I already did it.
Oh.
I did it too.
I'm going to go fast. I'm going to show you how you could have done it. Did you guys do it by hand or did you just use the calculator? Nice. I'm very happy about that. You guys get this? Yeah, and then you go y plus 2, y minus 1, and then you get y equals negative 2, y equals positive 1. You see how you could do that about as fast as the calculator? It'd be faster if you count all the entering buttons and pushes and all that stuff. Do it really fast, as long as the numbers are nice like those. Okay, anyways, no matter how you did it, we got our limits of integration. We're going from y equals negative 2, which is down here, up to y equals 1. Did I do that right, or did I? No, I got it right. There we go. Wait a minute. Hold on. Now that I look at this, you said negative 2 and 1? You know what? Oh, never mind. I confused myself with my own horrible notation because I was going fast. Never mind. We're good. Okay, so negative 2 and 1 are the limits of integration. Now let's address the high or low, because this is where we got to remember that we've turned everything kind of on its side. So no longer is it going to be high minus low. It's really going to be what? Right minus left. So right is kind of the higher edge. Left is the lower edge. So right minus left. For our region, which one is to the right? The curve or the line? The curve is to the right. So it'd be 3 minus y squared minus parentheses y plus 1. You would not believe how many people on an AP test forget to write stuff like those parentheses around the y plus 1, and they lose credit. It's called a presentation error, and it's pretty clear that they do know what they're doing. They just don't write it very well. So make sure you include those parentheses in there. I think at this point we'll leave this alone. This is a good spot to kind of stop as far as a setup goes. Pretty confident you guys could handle the rest of that as far as doing FTC 1 and evaluating. Allie, go ahead.
You said the first function is the one on the right, or?
Yeah. So when you go with a horizontal representative rectangle, the integrand is no longer top minus bottom. It has to become right minus left.
Okay.
Yeah. So that answers this question here. In this case, what would be the higher function? It would be the one that is further to the right. By the way, what would happen if you flip those around? What if you accidentally did left minus right instead of right minus left? Wouldn't you just get the opposite, the negative, of the actual area? So that would be a very fixable error. But you know, if you want to keep yourself from that issue, then you want to just go right minus left. Same thing with top and bottom. Yeah.
If both of those were on the left side of the y-axis, would you still do the farthest right function?
Yep.
Okay.
You would, for the same reason we talked about yesterday, where if both functions were below the x-axis, you'd still go top minus bottom. Same kind of reasoning. All right, good questions. Anyone else? Okay, cool. Let's flip ahead. Will you guys flip ahead to 7.2? Not normal shapes, things that are created by doing some interesting math. We're going to be first looking at what we call a solid of revolution. Solid of revolution is a three-dimensional object formed when the graph of a function, or the graph of a region, probably more specifically, is revolved or rotated around an axis of rotation. And so that's what we're going to be trying to visualize here. And so I want to give you guys something to try with the old Play-Doh. So let's do this. Let's take a function that we're all somewhat familiar with. Let's go with y equals e to the x. And let's take that graph. There it is right there, right? And let's do this. Let's cut this region off, say like maybe right here and right here. Therefore, we'd be creating a region that looks something like this. Trying to highlight it in green there. So what if we took that region right there and we rotated it around the x-axis? Let's think about that, what that would look like. Use your Play-Doh. Try to visualize it in your head a little bit. Just take that region and just mentally rotate it around the x-axis, and then try to make it with your Play-Doh. A chance to make a shape. Let's get into how we're going to use a little bit of math with this, and we'll go back to making the shapes here in just a minute. So to help how this gets formed, we're going to use what we call a representative disk. So I'm going to try to recreate what we just made Here is e to the x again, and we form the region, like roughly here and here. And so what we're going to do to try to visualize how this works, like where our formula comes from, I'm going to draw in a little representative rectangle, and I'm going to try to three-dimensionalize that for you. So if we rotate that disk, or excuse me, that representative rectangle, it'll create what we call a disk. See if you can picture this with me. Do you see the disk being made? If I were to draw it a little bit better, maybe the disk could look like this. You see that one a little bit better? So we're just going to be taking those little rectangles and revolving them around the axis of rotation, forming little disks. And so if you wanted to, you could take, I don't know if anybody has, does anybody still have their shape that they made? The little horn that we made earlier? Tess does. So one of the things that I like to do to kind of see the discs and everything, Tess, could you, let's see here.
Where's your floss?
I got it right here. Tess, could you take your pencil? Could you take your pencil and can you shove that right through where the axis of rotation would be? Does that make sense? You see what Tess is trying to do? She's putting the pencil right where the x-axis would be. So you go ahead and take that out. That's fine. I don't want you to destroy your shape because it was a nice shape. I'm going to use some floss. Oh, that was it right there. So, Tess, will you hold it so I can cut through it?
It looks like a volcano.
Oh, it does.
It does, doesn't it? Yeah. So if I were to slice through this, and then slice through again, and we just take it apart. So I just basically took my floss and cut through it. We take the top part off, but can you see the disc that's formed? Right? So we're going to call this the disc method. Do you see why? A disc is essentially like a CD or DVD. Do you guys know what the last D in DVD stands for?
Disc.
Disc, digital video disc, right? And so that's why this is called the disc method, because it uses these little skinny DVD-like things of varying sizes to create the three-dimensional object that you just made. So this hopefully will lead us to the formula that we're going to use. Really simply, it's essentially a cylinder, isn't it? Isn't a disc just a really short cylinder? And so the method called the disc method calls essentially for that. So I'm going to take this disc that we just drew over there, and we're going to talk about the different parts of it and how we could find the volume of it. The axis of rotation will be going through right there.
But there's actually no hole.
Nope, there's no hole. I'm just trying to show that's where the axis of rotation goes through. So I basically took one disc like I did with Tessa's shape, kind of pulled it off to the side. We're going to look at it. So what would you guys call this distance right here? That's the radius. That's right. So we're going to call that R. And essentially the distance from the center of the disc out there to the outer boundary of the disc. We're going to call that a radius. And then all this really comes down to is, do you remember from geometry class how to find the volume of a cylinder, or volume of a disc? It's the area of the base times the height. Yeah. So the area of this base would just be pi r squared. So we're going to write pi r squared times the height. And the height would be right here, wouldn't it? Wouldn't this be the h? But we're not going to call it h. Oh, I'm sorry, Mackenzie? No? Yes?
Wait, I'm confused. What's H?
So the h is,
The width of the disc?
yep, it's right, yeah. So the height, so this cylinder has been just turned on its side, essentially, the way that I've drawn it. So the height would just be a horizontal look on this one. But what are we going to call the height? You said it's the thickness of the disc, and so we want to have the thickness approach what? 0, because we want to perfectly fill the shape up with these little discs. And so to accommodate that, we need to call the height dx or dy, depending on how this thing is oriented. In this case, it would be dx. So volume equals pi r squared dx, or height, and that's where these formulas come from. So for a horizontal axis of revolution, volume equals essentially pi r squared dx with an integral on the r squared, right? And then for a vertical, it's going to be pi r squared again, but everything is going to be in terms of y. Please just remember, for the disk method, it's simply the volume of a disk, pi r squared times the height being dx or dy. Just remember circles, right? That's it. You all remember the area of a circle is pi r squared. We're just going to use that over and over again. Let's talk about what the different pieces of that are as far as the r of x and the r of y. And then we'll try a few examples. We'll get back into the Play-Doh, and hopefully we'll get really good at this. So as far as the pieces of the formula, r of x is going to be the radius in terms of x. R of y is the radius in terms of y. And then dx is the height of each disk. That would be in terms of x. And this is going to be the height in terms of y. So it's the same formula. One's in terms of x's, the other is in terms of y's. But bottom line is it's simply pi r squared h integrated over a particular interval. That'll give you the volume of the particular shape. This is where, like, I don't know if you ever wondered this, but like if you go all the way back to the basic formula we looked at, have you ever wondered where the volume of a cylinder even came from? It came from calculus, adding up an infinitely skinny number, or a very skinny infinite number of little disks added up gives you a cylinder. So anyways, we'll deal with that here in just a second. But let's go ahead and do some examples and break the Play-Doh back out. So let's take a look at this one. We're going to do two examples with the disk method. Here is the first one right here. It says, find the volume of the solid formed by revolving the region bounded by the graph of y equals cosine x and the x-axis on the interval 0 to pi over 2 when that region is revolved around the y-axis. Let's draw a picture first and then use the Play-Doh to make this. I will quietly graph. You graph on your own. Cosine instead of an actual circular shape, but it's pretty close to oh, there we go, Jasper. I think we all trust you again now. That's pretty good. So, guys, if you look back above in your notes a little bit, above in your notes it says the representative rectangle, the representative disk has to always be perpendicular to your axis of rotation. If you're going to use the disk method, there's another method you could use that's actually the other way. We're only going to use the disk method for us. And so that means my representative rectangle, my representative disk, needs to be horizontal, which means that the representative rectangle, the representative disk, is how thick? dy, right? The thickness is measured on the y-axis. This makes it a dy thick representative rectangle, which basically puts into motion the entire rest of the integrand, because that means that everything else needs to be in terms of y also, including the limits of integration. Everything's got to be in terms of y. So let's try to set this up. If I were doing a problem like this, if I were writing a quiz or a test or trying to take one of these questions and make sure it's good, here's what I would do. I would literally structure it just like this. So hopefully you'll take my advice. If you don't, you can take your own advice. I hope it works for you. I would go volume equals pi integral something squared dy. Because why absolute values?
Well, that's in the equation you gave us at the start.
No, those are brackets.
Oh.
It's all good. Sorry. So this is like for the disk method. Once you've decided it's going to be a disk method, isn't it going to be just like this? It's going to have a pi, it's going to have an integral, it's going to have a radius squared. It's either going to be dx or dy. So if you set this in motion right here, at the very least, you won't forget to put something in. I mean, you could maybe put something wrong in there, but hopefully you won't forget because you've given yourself little spaces to put everything. So let's go ahead and fill in the limits of integration. If I'm using these horizontal representative rectangles, I'm going to be accumulating from bottom to top on this region. So what would be the low limit of integration? Like where would I start accumulating disks? 0. Where would I stop? 1. So integral from 0 to 1, that would give me my starting point, right? Now I'm going to make this a little more complicated than maybe we would do at the end of something like this. But I want you guys to think about the radius here. And that would be the distance from the axis of rotation out there to the outer edge of the region. So I'm talking about from right here to right here. How far is that? It is x far, isn't it? Do you remember this from last year? Literally from the y-axis out to the right. Isn't that the very definition of what an x distance is? It's literally from the y-axis out to the right. It's x. So if you wanted to put an x right there, I think that actually shows a pretty good level of understanding. But it's the wrong notation, right? It's the wrong variable. What could I replace that x with that would be acceptable for all the other variables? How could I get there? What do you think? Yeah, it's going to be arc sine. Where are you guys, or arc cosine? Where are you coming up with arc cosine?
You guys solve for x.
Let me take a step back. Mackenzie, your question?
Oh, no, I'm just,
Okay. Anything you want to say? No, you're okay? All right. So you guys are taking this, aren't you? Oops, let me not cross it off. You guys are taking this, and what are you doing with it? Solving for x, right? So it's y equals cosine of x. So you do the inverse cosine of both sides, and you get this. And so we can replace the x that was in there with the inverse cosine of y. We know what the antiderivative of the inverse cosine of y is?
No.
We don't. It's not something we've looked at ever, is it? It's kind of weird because we've done the derivative of that, and we've done an integral that leads to something like that, but we've never actually done the integrand of that. So I would say at this point, we'd probably just use the calculator, use Math 9 if we had to go all the way to find the volume. So will you guys do that real quick? Take a moment and use Math 9, and let's figure out the actual volume. As easy as the Math 9 thing is, mistakes are made. So take your time, make sure you do it right. We'll compare answers.
Radian mode.
Thank you, that is right. Radian mode. Anybody watching the video be in radian mode? 3.586, okay. Do we all agree on that? 3.586 number?
Yep.
Is there any conceivable way that could be a negative number?
No.
Why not?
Volume can't be negative.
Volume can't be negative, and also the integrand is squared, right? So guaranteed whatever you have in there, the squared will turn it into being a positive. And that's a pretty important fact that we will look at a little bit later. Why don't you guys move on to number 2. What I think we ought to do is graph this again and then use the Play-Doh to try to visualize what the final shape would look like. I'll go ahead and draw a graph up here. It says the region is bounded by f of x equals 2 minus x squared and the x-axis. Find the volume of the solid formed by revolving that region about the x-axis. I don't know where that line came from. I think that must be a typo left over from some other question. So we'll just scratch that out. Okay, I'll do a little graphing up here. Please, you do the same. Take pen or pencil to your paper and graph this. Use calculator as needed. That's my region there. Feel free to compare whenever you get to that same spot. Tess, you got the cinder block wall going on back there.
Oh, because it's going to be like y.
Pretty impressive. If we just had like 1 million Play-Dohs, you could really make some awesome wall out of that. Take hours, but it would be worth it. And my 3-year-old would come by and knock it all over in 2 seconds and laugh. She's very good at that. All right, so we got that region. Does that work? This is looking ahead a little bit, but did anybody find the x-intercepts, or do you know what the x-intercepts are?
Yeah, root 2 number.
Yeah, plus minus root 2. So I'll put those in there. we'll need those later. So there you go. Now, we were told that we were supposed to revolve this around the x-axis, so I'll just put this little notation here indicating that. Let's remember that the representative rectangle has to be perpendicular to your axis of revolution, axis of rotation. And so that means instead of having a horizontal representative rectangle, this time it's going to be vertical, isn't it? So I'll draw that in there. We'll talk about the details and get this set up. So here is that vertical representative rectangle. The most important thing, or one of the more important things about that, is the thickness, right? The thickness of that vertical rectangle is how much? Dx. Instead of dy before, it's dx now. So it's going to be dx. And like before, that is going to set in motion the entire rest of the setup. It's going to have to be in terms of x instead of in terms of y. I'll show you again what I would do. And I think this is always something that I would listen to. Like if I do a question like this, literally I say, hey, look, it's a disk method. I'm going to set it up like this. Volume equals pi integral radius squared dx. I always start there, and then I fill in my limits, and I fill in my radius. As long as I do that correctly, I know that I haven't missed anything, I haven't left anything out, and I should feel good to proceed from there. So if you guys would start there, see if you guys fill in the radius, fill in the limits, and proceed, see how it goes for you, okay? Ready, set, go. Yeah, because isn't the representative disk to just accumulate from left to right? So it's going to start on that left edge, it's going to end on the right edge, so negative root 2 to positive root 2, I think makes a lot of sense. And what about a radius? Did you have one in there?
Yes, I had 2 minus x squared.
That's exactly right. So that's literally the height, that's literally the y, right? It's the height of the curve, but we want this to be in terms of x, so we put y equals 2 minus x squared in place, because we want to have the x instead of y for our variable. There is a different way that this could be done. If you were going to do this by hand, I have some wisdom to throw at you. I think you could have done this a little bit easier as far as the setup goes. You could use symmetry. Think about how you could use symmetry to make, if you had to do this by hand, you could make this a little bit easier. Any suggestions on how you could use that?
2 times 0.
Yeah, that's right. So this would be totally equivalent. Instead of going negative root 2 to root 2, you could go 0 to root 2. And you still have the same radius squared in there. But instead of pi, on the outside it would be 2 pi. The reason why it would be 2 pi is you just cut your domain for your limits in half. So if you just multiply the outside by 2, now you've recovered the fact that you cut it in half. You should have an equivalent answer. So that would be a totally equivalent expression. Would be perfectly good. Why would we bother to do that? There's a one-word answer. 0. Right? If one of your limits is 0, doesn't that always make things simpler? And so that would be worth, I think, doing if you had to do this by hand. Okay. Any questions? We're about to move on to some more interesting shapes. Okay, cool. Why don't you guys flip ahead to the next little section in your notes. So we're going to look at what we call the washer method. The washer method is essentially the disk method with a hole in the middle. So if you think about the shapes that we've made like 3 or 4 shapes so far. If you just punched a hole right out of the middle, wouldn't you be removing disks? And essentially that's what the washer method is. When we say washer, we are not talking about the thing that you wash your clothes in. We're talking about the hardware store washer. That makes sense? So if I was going to try to sketch that out, a hardware store washer would look like this. It'd have a little hole in the middle. Does that make sense? A disc with the center punched out. So I hope this makes sense to you. If we're going to use the washer method, if the washer method really is just an extension of the disk method, then the formula should look pretty similar, shouldn't it? Here it is. Volume equals pi integral of big R squared minus little r squared, and then either in terms of x or y. So R, capital R, big R, that would be the larger radius. Or you think of it as the outer radius. And then lowercase r would be the smaller radius. Some people would refer to that as the inner radius. It's all really the same thing. And then big R is going to be connected with the function that is further. Or far from the axis of rotation. Little r is going to be connected with the function that is closer. So we're going to use those formulas in a bit, maybe tomorrow. But let's do a little visualization with these to help us kind of understand the disk method, or the washer method, how it's connected with the disk method and what these things might look like. So if you haven't printed your notes out, you might want to print your notes out because I'm actually going to move on to this. So let's make an interesting shape. How about that? Let's go with I don't know, let's say that's like y equals x squared. And let's keep it interesting. Let's make another function. And we're going to say that this is like y equals natural log of x minus 1, I think that would be, shifted to the, or should be plus 1, shifted to the left one. There we go. That's not that important. Let's go ahead and take that region right here. We'll finish with a little bit of Play-Doh work. Let's take that region right there, and let's revolve that around the y-axis. Let's try to visualize with the Play-Doh what that shape might look like. A little more challenging, a little more interesting than those solid shapes that we've been doing before. This one's going to have a big old gap in the middle, right? It's going to have like almost a bowl feature to it. So let's think that through.